All right, so when we're graphing these logarithms, we first of all, we need to know what the logarithm without anything, what that looks like. So when you have the log, and I think that says 9, the log base 9 of x, we just want to know what the log base 9 of x looks like. Well, this is always, every logarithm hits the point 1, 0. Okay, every logarithm hits the point 1, 0, where there's no transformations, right? And then the other one that we're going to hit is if we plug in 9, log base 9 of 9, that would ask the question, 9 to what power is 9? And so the answer would be 1. 9 to the 9th power is 1. So just with these 2 points, we get a very good idea of what this looks like. My suggestion also would be know what the shape of the logarithm is. A normal logarithm without any shifting or compressing or anything like that, it's going to have an asymptote at x equals 0, and it's always going to hit the point 1, 0. Okay, so when we're going through here, we do not, yes, we do. We have 1 right here. Here he is right there. This is the logarithm without any transformations. Okay, so we know the shape is going to be going from the bottom to the upper right. So it looks like, if I had to guess, this would be y equals log base 9 of x. Okay, it goes through the point, and you can make these bigger, right? You can hit the pop out and make it much bigger, but this goes through the point 1, 0. And up here, it looks like it goes through the point 1, 9. So this one is the one without any transformations. Okay, so now the rest of them deal with transformations. So if this were on the exam, all right, and this was not a handpicked problem I had for our lecture today, but if this was on the exam, you will have transformations on there for sure, dealing with exponentials and logarithms, just maybe not in this format exactly. We want to deal with the nicer ones first, because then it eliminates some of the multiple choice, right? So here we have log base 9 of x minus 1. So this is the same thing, except it's down 1. So if it goes down 1, instead of being at the point 1, 0, it's going to be at the point 1, -1. So we're looking for a graph that goes through 1, -1 with this same shape, starting down and ending upper right. So starting down, ending upper right. Looks like this one is probably it. That looks like the point. Oh, this one right here. That looks like the point. Did I not write it? That looks like the point 1, -1. So it's the same thing as this one over here. It's the same thing as this one, except it's down 1. So that's going to be our y equals log base 9 of x minus 1. All right, what's next here? Well, let's take care of what happens if we have the -1 on the inside. If the -1 is on the inside, it's going to belong with the x. If it belongs with the x, it's going to do the opposite. So instead of going to the left one, this one is going to go to the right one. This one's going to go to the right one. Well, instead of the point 1, 0, we're going to go to the right one. So we're going to add 1 to our x. We're going to be at the point 2, 0. So we want to find the graph that has the same shape, that has an asymptote that's moved to the right one, and the point 2, 0. So it's going to be this one right here. See how the asymptote is moved to the right one? This one's going to be the log base 9 of x minus 1. That moves it to the right. That looks like a 2, but it's to the right one. All right, and if you have any questions at any time, please, please, please let me know. I would go through it for the nicest transformations to the hardest transformations. That's what I would do, because then there's less options. We are out of nice transformations. There are no more nice transformations. Everything else here has a reflection. Okay, so let's take care of this reflection here specifically. Sorry, I think there we go. All right, so we're going to take care of y equals log base 9 of negative x. This negative belongs with the x, belongs to the x. Everything that belongs with the x is horizontal. This is a horizontal reflection. We'll scroll down just a tiny, well, we can't scroll down a tiny bit. It's fine. It's a horizontal reflection. All right, we've got a horizontal reflection here. So it's this black graph, but it is horizontally, it's horizontally reflected. So it's going to start down here, go through here. This one starts out, well, depending on how you're looking at it, right? It goes to the left and it goes all the way down. So there's really only two graphs that do that, right? This is a possibility, the bottom right one, and the top left one is a possibility. Those are the only two possibilities based purely on the shape. So we want the one that goes through the point -1, 0. Because if we switch the x's and if we change the sign of the x's, we get -1, 0. Which one goes through negative? So this one looks like it goes through 0, 0. This one looks like it goes through -1, 0. So this one is going to be log 9 of negative x, log base 9 of negative x. So now since we looked at this one had the same reflection. I'm sorry, I think I hit something. There we go. Number 72 has the same reflection, but it's shifted. It looks like it's shifted to the right. So this looks like it's shifted to the right. Okay. Now, what's nice about problems like these, though, is you want to use the fact that you know number 72 has a horizontal reflection. There's only one other problem that has only a horizontal reflection. That's this one right here. So that has to be log base 9 of 1 minus x. Okay. That has to be log base 9 of 1 minus x. It's the only one that has just the one reflection. So looking at these two, we'll do them in blue. These two right here are the same, except one of them is shifted up 1. So let's take care of the one that's not the same. Let's take care of y equals negative log 9 and of negative log base 9 of negative x. That is both reflections. So this has both reflections. Well, the orange here is a reflection just over the x. So now we have to do the reflection over the y. What's that going to look like? It's going to look up like this. So there should only be one graph that goes all the way up and then all the way to the left, or starts all the way left and ends all the way up. And that is number 67. This one has to be negative log 9 of negative x. All right. And then we just have to worry. The difference between the blues is one is shifted up 1. So we can actually just look which graph is shifted up compared to the other one. This one is shifted up, the number 68. And so it's going to be 1 minus log base 9 of x. And then this one is just negative log base 9 of x. Because the difference between the two is just shifting. On a problem like this, use the fact that it's multiple choice to help you solve it. Typically problems like this, where like you can use parts of the question to help you with other parts of the question, are not on your exam. Something like this would not be a very good exam problem, but it is a really good problem to get you thinking about transformations and how the graphs of logarithms look. All right, we're going to pause here. I'm going to pause here, see if there are questions. All right, so we're going to use the given function to answer parts A through F. Here, f of x equals the natural logarithm of x minus 2. Okay, and just to make things a little bit bigger, I'm just going to write it out. Natural logarithm of x minus 2. And part A is asking to find the domain. All right. And domain of logarithms is almost the same thing as domain of square roots. Domain of logarithms is the stuff inside the logarithm, the stuff that you're taking the log of, has to be greater than 0. Okay, it has to be greater than 0. Now, with square roots, it has to be greater than or equal to 0, but you can't take the logarithm of the number 0. You can't take the logarithm of negative numbers, and you can't take the logarithm of 0. So that's why it has to be greater than 0. So for us, what we're taking the logarithm of is x minus 2. That is what we have to set to be greater than 2. And because it says enter your answer in interval notation, x is greater than 2 is not our answer. We need to put that on a number line. And on the number line, we're going to put 2, and the arrow points to the right. It's a parenthesis going to the right. The interval notation is 2 comma infinity. That would be our answer for this one, 2 comma infinity. Okay, and I'm going to share my screen here where I'm entering the answers. I'm going to give everyone just a little bit more time to take notes. Now we're going to jump over, and we're going to jump over to the wrong one. It's not the one I wanted to share. So let's jump over to the correct one. The correct one is this one. So the domain is going to be 2 comma, and then we use the infinity symbol down here. All right, we're going to check our answer. Excellent. Gives us some positive feedback, which is nice. Now we're going to select the graph. Okay, so this is where on problem 44, we were able to use the graphs that were given. This one has less graphs given, but we're going to graph this first because this is a very appropriate problem to just graph. Okay, so part B, it wants us to graph. The way I would do this is by straight transformations, only thinking about the shape. A graph without any transformations, a logarithm with no transformations will go through the point 0, 1. And it will have the asymptote at x equals 0, Our graph, because the -2 is on the inside of the parentheses, it belongs with the x. If it belongs to the x, it does the opposite of what you want. Instead of subtracting 2 to your x values, it adds 2. So we're going to the right 2. So if we're going to the right 2, this x equals 2 is now going to become, this x equals 0 for the asymptote becomes x equals 2. And this point, 0 comma 1, which I of course mislabeled, please don't write it as 0, 1. It's
I don't know
1,
if it's
0.
just me. Excuse me. I don't know if it's just me, but I'm just seeing like I'm not seeing you write anything. Am I supposed to be seeing something?
Yep. Yeah. Thank you so much, Tish.
Sorry, I'm just seeing like A, B, C, and D with graphs.
There we
Thank
go.
you.
I'm sorry.
There we are. All right.
I'm
Thanks.
sorry. Let's go through it again too. We're going to go through it again. And I'm going to give more space. Thank you so much, Tish. I really appreciate that.
No problem. I was just waiting and I didn't know if it was just my screen or not.
So, and this is great because now I can fix the issue that I had and no one really saw it. So, well, it's not great. It's never great to make a mistake in front of other people. It's okay. You get to make mistakes.
How you learn. It is awesome. That's how you learn.
It is how you learn. Making mistakes is how you learn. I'm supposed to know it. So making mistakes when you're an instructor in front of people is bad. Making mistakes when you're practicing your homework, not a problem at all. So if we were just to graph without any transformations, in fact, let me get rid of everything I just made a mistake on. There we go. Even though, okay, so if we were just to graph the natural log of x, right? Y equals the natural log of x. This will go through the point 1, 0. And it's going to have an asymptote at x equals 0. That information right there, that should be memorized. Having the basic knowledge of what a logarithm, where it goes without any transformations, should be memorized. Then we want to deal with the transformation, which is it's the natural log of x minus 2. This is going to shift everything to the right 2. It's a transformation that belongs to the x. If it belongs to the x, it does the opposite. So we're going to take our graph and we're going to add 2 to all of our x values. So our new asymptote is going to be at x equals 2. And we're going to go through the point 3, 0. So ours looks like this. It's the same thing shifted to the right 2. It's the same thing, but it's shifted to the right 2. And especially with my math lab, it's super helpful to have like an actual point that we know it goes through. The graph goes through the point 3, 0. There's probably only one graph that goes through there, but I'll take a look at it. So we're going to reshare now, because some of the problem with is entering things, right? But this one is right. And we could use the fact that it's multiple choice to help. Can we see these if I hit the pop out button or no? Yeah. Does this graph go through the point 3, 0? No, no way. Does this graph go through the point 3, 0? Ooh. It does not. It's close because each tick is 2. So it goes through the point 2, 4, 6. It's a little bigger than 6. So that's not it. Does this one go through 3, 0? Yeah, go ahead, Tish.
Yeah.
Yeah, this one's yes. This one goes through 0, 3, 0 because each tick is 2 and we're in between 2 and 4. In between 2 and 4 has got to be 3. C is our answer. Okay, we'll check it. Excellent. From the graph, determine the range and any intercepts of T. So let's go back and reshare our work so we don't forget. So what we want next in part C is the range, and we have the graph, and we want the intercepts, or asymptotes. Oh, wait. Am I lying? Did they actually say, hold on, did they? No, they said asymptotes. Okay, good. I didn't want to be lying. Asymptotes. Okay. So what's our range? The range of every logarithm function will always be the same. It'll always be negative infinity to infinity. Well, okay, that's not always true, but it's always true in this class. It's always true in this class. The range is going to be negative infinity to infinity. Wait. Yeah, that's fine. All right, that's fine. The asymptotes. What are our asymptotes? Well, the asymptotes started at x equals 0. And then because we moved everything to the right 2, our asymptote is going to be x equals 2. When entering it into my math lab, we want to make sure to put x equals 2 because an asymptote is a line. All right, so let's share the this right here, and we're going to enter our answers. So the range of every logarithmic function is the same, negative infinity to infinity. So parenthesis, negative, and then infinity, comma, and then infinity again. And then check. All right, excellent. Now there is a vertical asymptote. All logarithms have a vertical asymptote. Okay, so I was trying to remind you to put x equals 2. This was nice of the problem in the fact that it said the vertical asymptote is x equals, so all you have to put is 2. If you put x equals 2, it'll be x equals 2. Okay. So now we're going to find the inverse function. So our job is to find the inverse function. Let's go back to our whiteboard and we're going to find the inverse function. We're going to keep the graph, but we're going to get rid of the range and the asymptotes. All right, so we're doing inverse. We're going to find the inverse. And the way we find inverse functions is you change the f of x to y. So we're going to start with y equals the natural log of x minus 2. And then you change everywhere you see y, you write x, and everywhere you see x, you write y. Okay. Now, it's also what we need to know is that anytime we have a natural log, that means log base e. So we get x equals log base e of y minus 2. I'm going to replace it because when we solve logarithms, the way that we solve logarithms, because our job now is to get the y by itself, right? So I probably should have said that earlier. The way we solve logarithms is we get the logarithm by itself, and then you rewrite the logarithm as an exponential. So the way that we rewrite, the base of the logarithm is always the same as the base of the exponential. So this is going to be e to the power of. Then you go to the opposite side of the equal sign. So e to the x power is going to be equal to, and then you bring it back to what's on the inside, y minus 2. Okay, I'm actually going to pause here. I should have been pausing more often. So now the y is almost by itself, right? Our job is to solve for the y. We just need to add 2 to both sides, and the y will be all by itself. Oh, the function then becomes e to the x plus 2 equals y. This is, well, and we should replace the y with the inverse function notation. F to the negative 1 of x means the inverse of x, or of f, is equal to e to the x plus 2. That's what we're going to enter for our answer. So let's go ahead and share the my math lab, and we will do that one right there. So in order to do that, we're gonna, can't scroll down yet, but it's going to be e, and then we can hit this exponent button right here, e to the x, and then we have to like arrow over and then put our minus 2, because the minus 2 is not in the exponent, it's on the outside of that exponent. Oh my gosh, I messed up, because I put minus 2. Our answer was plus 2. Sorry, thank you. I think Nick or someone else was letting me know that it's plus 2, not minus 2. All right, there we go. Perfect. So now we're going to find the domain and the range. This is an extremely important topic in this section, is about the domain and range of the inverse functions. Okay. So new share, we're going back to, there we go. We're going back to our whiteboard. So it asks for the domain. Okay. The domain. The domain of any exponential function is always negative infinity to infinity. Okay. However, we should also note, because you will be tested over this multiple times on your exam, that the domain of the function is equal to the range of the inverse. Okay. And then the other way as well. The range of the function is equal to the domain of the inverse. They're just switched. They're just flip-flopped. So because we already knew the range from the graph, the range of the function was negative infinity to infinity. The domain of the inverse will be the same. Okay, so now we can talk about, well, what's the range of the inverse? What's the range of this function? Well, you could graph to find the range, but a better way is what we did. Take what we had in the first part of the problem, where it asked for the domain of the function. The domain of the function was, I'm sorry, it was positive 2. It was positive 2 to infinity. We got that from part A. And when I bring up the my math lab, the domain of the original is 2 to infinity. The range of the inverse is then 2 to infinity. This is the inverse function. The regular function, then they're switched. So the domain of the regular function was 2 to infinity, and the range of the regular function is infinity, negative infinity to infinity. So let's go ahead and share, and we'll plug that in. That right there is an extremely important concept that you are tested over multiple times. Multiple times you were tested over that. So find the domain and range of the inverse. This is asking for the domain of the inverse. The domain of the inverse is the same as the range of the regular, which is negative infinity to infinity. Recall that the range of f, what's the domain? I missed a negative sign. That's what I did. Sorry, thank you. Perfect. All right, and then the range, this one was the 2 to infinity. All right, graph the inverse. Oh, so the last one, we had one more. So we're going to graph the inverse. Oh, that's why I left the graph of the original up. So we're going to share screen. We're going to go back. Okay. And we're going to clean this up. Okay. Let's just this is what we got for the regular function. Okay. The regular function, I think we did it in green, so we'll do it in green again. By the regular function, I mean this was the natural log of x minus 2. Okay, so what we're going to do in red is graph e to the x plus 2, which is our other function, right? Is our inverse function. Well, this is an exponential function. Exponential functions have a y equals 0 asymptote, and this is going up 2, and it goes through the point 0, 1. So normally we would go through the point 0, 1, but because we're going up 2, we're going to go through the point 0, 3. And our asymptote is normally at y equals 0, but since we're going up 2, we're going to be at y equals 2. So our asymptote is going to be at y equals 2. That's right there. And we're going to go through the point. I don't want to do this in red. Let's do it in blue. Dark blue. Dark blue, good. 0, 3 is the point that we're going to go through. This is what we're going to look like. Something like this. Okay. Now, if you are an absolute amazing artist, okay, you can fold, okay, and I'm not a great artist, as you probably already knew. You can fold. What happens is if you fold the function over the line x equals y, you should get the inverse. So if you picture yourself folding that over the diagonal, it's supposed to land on top of itself. I'm not a perfect artist, so mine doesn't look exactly right, but hopefully you can get the idea of how that can look. But either way, it doesn't matter because we're not graphing, we're matching. So we need the one that has an asymptote at y equals 2 and goes through the point 0, 1. So we need the one that goes through the point, well, and we got to pop them out, right? There's no way we can see without popping them out. Well, that's below the x-axis, so it can't be A. What about B? B goes through the point 0, 3. I don't think so. B doesn't look right. What about C? C goes up too high. That's like up at 8. What about D? Oh, D. And in fact, D is the only one that had the asymptote in the right spot. So D is our correct answer here. There we go. So we finished that one up. Can we go back and see all of our answers? Are they still there? Yeah. All right. This set of skills where you have to find the domain of a function, where you have to graph the function, then give the range of the function, and then do the same thing for the inverse. This set of skills has been highly emphasized. On the exam. Okay, so please be sure that you can go through a problem like number 45. All right, so we're going to go a little bit of an explanation into logarithms and how we transform logarithms back into exponentials. And I think the most fundamental way to start with that is with something we're comfortable with. We're used to seeing 3 squared equals 9. Now, if we change this to a logarithm, this will be log, right? Because with a logarithm, you have to have the word log. And the base of the logarithm is always the same as the base of the exponential. So here the base of the exponential is 3. So the base of the logarithm is also 3. Then you go to the opposite side. Log base 3 of 9 is equal to 2. That's how we rewrite it. Now, you have done this before. I'm always a little hesitant to bring in multiplication division because it's the relationship between multiplication and division is the same as the relationship between exponents and logarithms. Okay, you've done this before, but you haven't done it for a very, very long time. You got to think back to maybe 3rd, 4th, 5th grade, somewhere around there, maybe 2nd. I don't exactly know. You used to do, you knew really good. You knew really good that 3 times 4 was 12. You were a professional at 3 times 4 equals 12. Okay, but then, right, as math always does, they pull the rug out from under you and say, okay, well, 3 times 4 is 12. What's 12 divided by 3? And when you were learning how to do 12 divided by 4, because now you can't remember because you just know the answer is 4, right? You would ask yourself, 3 times what equals 12? That's what you would do. And the answer there is 4. You can rewrite a division problem as an you can rewrite a division problem as a multiplication problem. And why do you do that? Because multiplication was comfortable to you. You were really good at it. We do the same thing with logarithms. You can change a logarithm back into an exponential. And the reason why you do that is because it's more comfortable that way. We are better at exponents than we are logarithms. Now, if we stuck with logarithms, we'd be just as good at logarithms as we are with division. Just usually we don't stick with logarithms that long, okay? So let's get to the essence of the question. If we have a logarithm, in fact, I'll just scroll down so we still have that. If we have a logarithm, let's say log base 3 of 64, okay? Now, this logarithm does ask a question. In fact, I would normally, I mean, there's not enough time to actually lecture in this lecture, right? We have an hour. But if I were doing a lecture to my virtual students or my students in the classroom, the question this logarithm asks is 3 to what power is 64? 3 to what power? Oh, and it doesn't even work, right? So can we change this so it does work? In my head, it worked, but we'll change it to 4. So we'll change it because now 4 has an answer. 4 to what power is 64? This has an answer. Log base 4 of 64 is equal to 3. Why? Well, let's change the logarithm to an exponential. 4 raised to the 3rd power is equal to 64. All right, I'm actually going to pause here. Time. All right, so when we had the problem, x equals the log base e of y minus 2, okay? Now, it's not a division problem. This is not a division problem. What we're going to do is pretend. We're going to pretend that the problem was x equals y minus 2 divided by 3, okay? If this was the problem, you could use the definition of division. This is super weird, but this is okay. What does this mean? This means 3 times what is y minus 2? Well, you can rewrite this. What is 3 times what? You can rewrite it. What's that mean? That means 3. Well, we know what the what is. The what's x. 3 times x equals y minus 2. You could do that. No one in their right mind will write out the definition of division and then use that to do this. What are you all going to do on this problem right here? And I'll pause for this. I'll pause for it. And by the way, once you multiply both sides by 3, you get 3x. equals y minus 2. Once, what the book does and what students typically like the most is we're using the definition. What does the log base e of y minus 2 ask? This asks e to what power is y minus 2? Well, e to what power is, well, we know the power. The power is x, so that's e to the x equals y minus 2. Now, this is fundamentally different. Solving for y is fundamentally different than the way we do it with multiplication and division. It's only fundamentally different in the way that we think about it. It's actually the same. How do we get rid of a logarithm base e? Okay, and in fact, I'm going to make more space and get rid of our, right, because it is important. And one kind of, well, I know this is probably not that helpful for answering questions on homework, but that's not all of this lecture is supposed to be. We're supposed to answer questions too that students have. So x equals log base e of y minus 2. How to get rid of log base e? Okay, it's a little bit weird. To get rid of log base e, you apply a base of e on both sides of the equation. So you're going to take a base of e, and then you're going to write the left side of the equation. And then you're going to take a base of e, and you're going to apply it to the right side of the equation. Log base e of y minus 2. What happens? Well, on the right side, e raised to the log base e power cancels each other, just like multiplication and division cancel each other. Exponentials and logarithms cancel each other. And on the left side, nothing changes. It's e to the x equals y minus 2. Okay? This is how we solve if it was addition, subtraction, multiplication, division. If it was an exponent of 2, right? We take the square root on both sides. How do you get rid of an exponent of 2? You square root both sides. How do you get rid of an exponential? Or you apply a logarithm. How do you get rid of a logarithm? You apply a base, an exponential as a base, right? All right, let's pause here. Let's see if that answered the question. All right, anytime you're graphing an exponential, and here we have transformations applied to it, but let's pretend we didn't have transformations. An exponential is always going to have a horizontal asymptote at y equals 0. Of course, we're talking about no transformations. It always goes through the point 0, 1. That is always going to be good enough for us to graph. All right. This plus 1, what does it make it do? It goes up 1. So we just need to move the y values up 1. So our graph is going to have an asymptote at y equals 1 and go through the point 0, 2. Okay, so we want to remember this. And if you write that down, I'm going to share the screen and go over the graphing tool because it's really, well, we'll see if I can get it. It's not super intuitive. So, all right, we're going to click to enlarge the graph. Okay. And what you want to do is select the exponential tool. This first one is the way logarithms look. This, in fact, you can, well, I don't know if you call it cheating, but right here it says logarithm tool. So you know that's not what we're using. So let's go to the other one that says exponential tool. Okay, so ours is an exponential tool. And well, let's see what it does. I don't know what it's going to do. There we go. I just put it anywhere. It doesn't matter where you put it. In fact, we did a whole bunch of stuff we didn't need to do. All we have here is a vertical shift of 1. That's literally all we had to do was make a vertical shift of 1. Hold on, time out. Can you go back to this? Nope. Go back to the, there we go. It pops up. It was a vertical shift of 1, although, is mine a vertical shift of 1 right now? It is. On the number line, it is 1. This is a terrible tool. It's a terrible tool. Sometimes you may also have to change the base, but it put in the correct base for us, which was nice because we don't want to miss a problem because we thought it put in the correct base and it didn't. All right, let's save that. Let's check it. All right, what is the domain here? The domain of is always the same. It's how far left, how far right. This domain is negative infinity to infinity. Every exponential function has a domain from negative infinity to infinity. All right, this time I remembered the negative. Improvement is always good. Let's check it. And now it should ask us about the range. So the lowest value is going to be your y-intercept, or your y-asymptote, your horizontal asymptote, which was 2. No, not 2. It was 1. It was 1. And then it goes all the way up to infinity. You can also see it on the graph. Just look in the graph. How low does it go? The lowest point is 1. The highest point is infinity. All right, determine the horizontal asymptote. Well, I mean, they could have asked us about this before. The only thing we have to be careful of, wait, it has 1. The thing that we have to be careful of is this one did not say y equals. So we have to put y equals 1. Now, these problems are very inconsistent, and that's a problem with my math lab. If problems arise like this on your test and you go look through and you say, oh my gosh, I missed a problem because I put 1 instead of y equals 1. That's something you should email your instructor about. Say, you know, I put in the right answer, but you know, on some problems it asks for the y equals and on some of them it doesn't. What's the y-intercept? The y-intercept, you can see it on the graph, is 0, 2. Is 0, 2. So please don't be afraid to email your instructor when things like that happen, because my math lab is not perfect. Okay, and I'm not perfect either, because it said type it as an integer. And look at me. I typed it as an ordered pair. Again, sometimes my math lab wants an integer. Sometimes it wants an ordered pair. It does let you know when, but we don't need to be perfect at my math lab to be perfect at math. All right, that was the total question. Let's pause this one here. See if there's. All right, so this is homework. I should have wrote down beforehand, sorry. It's homework 6B, number 7, okay? 6B, number 7, it's 2 to the power of 4x plus 1 equals 4, okay? And I am, so if that's all right, Nick. Hopefully we won't have to worry and we're not gonna, you know, we'll make it through this semester. All right, so sorry, I should have shared. I didn't share. Should be sharing now. Yeah, there we go. Messed up the sharing. All right, we got homework 06B, number 7. It's going to be 2 to the 4x plus 1 equals 4. Now, it's a little bit weird because we know about logarithms now, but when this was covered, we didn't know about logarithms. So the way that I would always say to solve this problem is get the same bases. Get the same base. Okay, so 2 to the 4x plus 1 has a base of 2. Can we write 4 as a base of 2? Well, yeah, 2 squared is equal to 4. And now once the bases are the same, you can set the exponents equal. Once the bases are the same, set the exponents equal. All right, set exponents equal to themselves, right? So it's going to be 4x plus 1 equals 2 squared, not 2 squared, just 2, just the exponents. Subtract 1, 4x equals 1. Divide both sides by 4, x equals 1/4. The way it wants us to write our answer is as a simplified fraction. So we're going to enter it as 1/4. Okay. Now we can apply logarithms since we know what they are. Once we have the same bases, what are we going to do? Just take log base 2 on both sides. Then what happens? Well, the log base 2 cancels with log base 2. Log base 2 cancels with log base 2. And what are we left with? The 4x plus 1 equals 2. That's why you can just set the exponents equal to each other. We can apply the We can apply the logarithm on both sides. All right, let's pause here.